with all the problems from chapter 10. For those who didn't have me before, and even for those who had me, please read the text. Please read the textbook. So let me explain how I would study if I were you. You have the problems, but you have also the section number, okay? That section number, if you're struggling with that, it means you need to read, the answer should be in the section, in that section. So how do you get to the answers? Because I'm not giving you the answer key. In that section, you have questions that I gave you the answer key for. So when you look at, let's say, chapter 10, section 4, into section 4, there are some questions that are written right there inside the text. So you try them and check the answer key that is also posted on Canvas. So I gave you the answers to all the problems in every section of the book. So if you're struggling with any problem from the pretest and it's a part of a specific section, go try the questions in that particular section. Is that clear? Is everybody understanding this? Yes.
What chapter are we doing?
The test? On the chapter what?
I'm saying what chapter are we going over today?
10. We're going to finish 10. Any questions about the pretest? Is everybody clear? Okay. So last time on chapter 10, we talked about alcohols, and we said that they undergo substitution. Remember, it needs an acid. So we started with Bronsted acid, then we did the Lewis acids. Then we talked about elimination that also requires what? Acids. And I told you that elimination is also a headache because it can give you more than one product. Then we talked about oxidation reduction reactions. And the oxidation reduction, the good thing about them is you don't have to know the mechanism, but you have to know that the only difference basically is primary alcohols can go all the way to carboxylic acid. Secondary can only give you ketones, and tertiary don't get oxidized because they don't have hydrogen, okay? And that's what you're gonna see on Wednesday in the lab. So in the lab, you're gonna do some oxidations. You're gonna mix it with some strong oxidizing agent and check what happens with them. So I'm giving you already a hint for those who are in my class about the pre-lab. If it's primary alcohol, what do you expect as a result of an oxidation? If it's secondary, what do you expect? If it's tertiary, what do you expect? So today we're going to talk about ethers, okay? So what are ethers? You have two types. You have the linear ether. So we have the R, O, R prime. And by the way, I put OR prime just to show sometimes they can be the same alkyl group, sometimes they can be different. So if it's the same, it's easy. If it's different, then there are some little differences between them. Now, how are they produced? Ethers are produced by the addition of alcohols to alkenes. And that I told you to look at the appendix in the end of the book. Remember, for each functional group, you have to have a page where you put here ether, and then from the back of your book, you show me how you produce it. What are the different methods? And there can be many chapters, so if it's in the previous chapter, you write them anyway, and then make sure you write the chapter so you can go and remember the mechanism. If it's a chapter that we already did, I'm not going to teach it. But if it's a chapter in the future, you will be, you will understand the mechanism later. But you have to get started with these charts right now. Don't wait until the last minute. Is that clear? So we did also the alcohol, so make sure you write all the different methods of preparation of alcohols. And today, all the different methods of ethers, epoxides, and amines, and thiols. So we already know that alcohols are not very reactive, okay? So how about ethers? If I put a Bronsted acid here, what should happen here? I'm just trying to see what I learned from alcohols. So if you put a Bronsted acid, what should be the reaction? Inflammation, okay? It's always a protonation because the oxygen is a nucleophile, okay? So you end up with R, O, H, R prime, plus X minus. Now, if this were an alcohol, what is the second step? Because you already studied this. What would be the second step? Which is normally what? Water, you agree? So water will leave and the halogen will attach. So here, what will leave then? What will leave? An alcohol would leave. You agree? So we have two options. So I'm going to show you. Are you seeing which options do we have? We can have this leaves and the X attaches here, or this leaves and the X attaches here. Are you seeing this? You have two options, either the halogen attaches to the left or to the right. So let's try with the blue. Let's see the blue, this comes here, this takes off. Okay? So we end up with R, X, plus HO alcohol. Okay? But I can also have a green option. So this can come here and this opens. So the green, so this is the blue, and the green will give me R OH plus R prime X. Do you see this? So the question is, which one would work best? Of course, here, if I put R and R prime, I'm assuming they're not the same. You agree? Yes. So the question is, if you have two options, which one works best? The answer has to do with steric hindrance, okay? Now, what halogen works for these reactions? Remind me, which one works the best?
Bromine and iodine.
It has to be really strong acid, so it should be bromine and iodine. How are they compared to fluorine, let's say? They are big. So because they're big, which side would be easier for them to get into?
The less bulky.
The less bulky, so the less sterically hindered. So we don't have both. We only get the one that gives you the halogen. So the X has to attach to the less sterically hindered, the more, exposed. If it's not exposed, the halogen would have a hard time getting there. Okay? So here, the answer, I don't know which one, the top or the bottom. All I can tell you is the halogen attaches to the less bulky. That's all you have to remember. Okay? So the one that's really small, less bulky, that's where the halogen goes. Makes sense, doesn't it? It's really a matter of like, do I have room to get it, to make my way there? If I don't, then I'm not gonna attach. Okay, so this is using what? We use the Bronsted acid. So everything we did with alcohol, I wanna show you by comparison what happens with the other functional groups. So what is the next option? If it's not a Bronsted acid, what can I use? Lewis acid. And it's all to help you also when you write your summary, your notes, like try to kind of be consistent with the approach so it helps you know how are they similar and how are they different. That's the only way you can remember all of these things. It's how are they similar, how are they different. So let's put something else. Okay, so what is the other one? Let's try the Lewis acid. So I'm gonna use the sulfonyl chloride, just any one of them. You agree? Anyone would work. So let's see if I use the SOOR something NCl. And remember, we have a lone pair. I like to show that lone pair to show that it's a Lewis, empty orbital to show that it's a Lewis acid. So the first step is this attaches here and this leaves. Remember, for Lewis acid, you always have the halogen leaving. And I'm just doing it over and over to help you remember that Lewis acids are different from Bronsted acid, and there is always a halogen that leaves. So you end up with R, O. So here, I'm going to just put the R prime at the bottom, so I have space here. It's going to be S, O, O, R prime, R, and then Cl minus. So what is the next step if we had an alcohol? What was the next step? The pyridine. What does the pyridine do? Deprotonate. Is there anything to deprotonate here?
No.
So this doesn't work. Okay? So the only way Lewis acid to work is you have to deprotonate after they attach. So this won't work because there is no hydrogen to deprotonate to create the reaction. Okay? So that's cool, easy, you see? So at least it shows me that ethers, how many reactions I have to remember? Only one. Do you think they will oxidize?
No.
What does it take to oxidize an alcohol? You have to have a hydrogen on that carbon carrying the O. Okay? We don't have hydrogens there. So ethers are not going to be oxidized. So ethers are very stable compounds. That's the reason we use them as solvents. Okay? Ethers are very stable, meaning they don't react. They only react with the Bronsted acid. Clear? Okay. Now, next question, next one is what? See how easy the chapter is looking now? The alcohols, we did all of that work and it looked like, oh my God, we spent too much time on only one functional group. What happens to the others? But what's next? What's the substance with oxygen that we need to study in this chapter?
Epoxide.
Epoxide. So let's look at epoxide. So is everybody understanding this? Ether will react with what?
Bronsted acid.
Will they react with Lewis acids?
No.
Why not?
There's no H to deprotonate.
There is no second step, has to be deprotonation. They're not going to deprotonate. So no reaction. And then for elimination, remember also elimination, what does it take to do an elimination? You need a Bronsted acid like sulfuric, but you have to remove. So actually I have something about elimination. They don't do elimination because of the leaving loop. So yeah. Yeah, for now, just think of like, they don't do elimination. They only do that. Let's look at epoxides. So an epoxide is this. Okay? Still has a lone pair there, but we can have, this is a plain epoxide CH2, the simplest one. But we can also have substituents, okay? So here, I can put a methyl on one side and nothing on the other, for now. We can do all the reactions with the simple one, which is kind of boring, it's easy to predict. But let's try with something substituted like this. So what are the reactions? Just like ethers and alcohols. In this case, what type of compound is this? Is this an acid or a base? It's a base, just like ethers, they have lone pairs. So can I add a base here?
No.
We'll see. Can ethers react with a base? No. They only react with Bronsted acid. So here, let's start with an acid. So if I bring HBr, okay? What's the first step? Always protonation. This is a nucleophile, this is an electrophile, this is a base, this is an acid. It's always protonation. So this takes the H, this takes the lone pair, the bond. So you end up with this. The oxygen is positive. Okay? And then we have the Br minus. So here, what are my options? The Br has to attack, you agree? But before I even start here, what is the hybridization here? This one. SP how many? 3. This is an SP3. How about this one? What's missing on the structure here? 2 hydrogens. It's also SP3. What should be the angle for SP3? 109. What is the angle here? What's this angle? 60. Is that good? It's supposed to be 109. And what are we doing? We're saying you stick right here in the 60. So is this a stable ring? It's extremely what? Unstable. By the way, if I put another carbon here, it won't even last. So epoxides are extremely what? Unstable. Unstable means what?
Reactive.
Absolutely. That ring is waiting to pop open. Anything will pop it open because it's really a 109 that is now forced to be a 60. Is everybody understanding this? All of this is not described in the chapters. I'm giving you the added value for you to remember. I don't want you to just say, oh, I know epoxides are more reactive. By the time you get to chapter 20, you're going to be like, oh my God, I forgot what it was. Why? But now you understand. If you understand, you will remember it. If you don't understand, you're not going to remember. So what is the answer? Why are they very reactive?
They're unstable due to the restriction of the.
So they have an sp2, sp3 carbon that is supposed to be what?
109.
109, but it has an angle of 60. So what do we call that? We call it angular strain or ring strain. So that terminology of ring strain, it's like too much pressure, too much, compression on that ring. So there is a ring strain because it's supposed to be 109 and it's 60. So what does it mean? It means that that ring is ready to what? Pop open with anything. Just set me free. It's too tight here, okay? So now it has to open. So what are my options here? It's gonna open on which side? So we have 2 possibilities, you agree? And not only 2 possibilities, we can have it in 1 step or 2 steps. Okay, so the question is it 1 step or 2 steps? If I attack on this side, everybody seeing this? So it's almost like a primary alcohol, you agree? So what is here? This is a CH2. So this is kind of a primary. So what would be the mechanism?
One step.
One step. This comes here, this opens. So what do we get? We get a Br, and then the C, so this, and then this, with a methyl, and then an OH. Do you see it? So if I number them, so you can keep track of things. So this is my 1, my 2, this is 3. So, sorry. So this is 1, I'm missing something. And yeah, the 2 is here. The 2 has a methyl. And then there's an OH. So this is my 2. And this is 3. So that's good to number them, to keep track, so you're not making mistakes. You see, I made a mistake. So this is simple. It's an SN2. Because if it happens in 2 steps, the carbocation is going to be primary, so it's not stable. But let's look at the other side. So what can happen here is this open, and we can end up with what type of carbocation here? Tertiary? Secondary. So still secondary, better than primary, but is it really stable? No. So maybe what I should do is to make it interesting at the first step, and then we'll come back. Okay, I'm not trying to skip this, okay? So we have here 2, 3, 4. So here, I'm gonna have this, okay? 3 and 4. Is everybody with me? Now, if I have 2 carbons here, and that opens, what do we get? This one would be what? Tertiary. So, again, I'm going to call them 1, 2, 3, 4 to keep consistent with the previous scenario. So now the OH is on the 1. That's my 1. And then 1 is connected to 2. And on 2, I have 3 and 4. So this is 2. This is 3. And 4, and it's positive. And that's a pretty what? Very stable what? Carbocation. So this would be 2, 3, 4. And then the next step would be Br minus will come attached to the carbocation. And we end up with the very different product from the previous one. So the question is, which one is better, the top or the bottom? Why? If you don't know why, you don't know. You don't know. So here, this carbon is what? sp3, which is what? Tetrahedral. So the bromine has to come to a carbon that's tetrahedral. Remember the hybridization? I told you that hybridization explains how hidden or exposed the atom is. Okay? But here, what's the hybridization right here? sp2. So what is the shape here? Trigonal, planar. So this is pretty flat, so the bromine has plenty of space to attack. So bromine will always attack, the halogen will always attack to the most substituted. Always. The more substituent. Why? Because it goes through a carbocation that's more exposed. So if you're going to form a carbocation that's exposed, then that is the better product. So the halogen always adds to the most substituted carbon. Again, why is that? Because it goes through a stable what? Carbocation that is trigonal manner, more exposed. Now, how about if we use a Lewis acid? What's the difference between Bronsted acid and a Lewis acid? It has an empty orbital, but what's the difference? Here, we had to protonate. The Lewis acid will attach to what? To the lone pair of the oxygen. You agree? So if it attaches here, so instead of H, you have your Lewis acid here. What is it going to do? It's usually even more what? Bulky. You understand? So where is the attack going to happen? This is bulky. This is bulky. The halogen has to attack this. So it's all about like bulkiness. Lewis acid usually, like you have a sulfur with 2 oxygen and all of that stuff, that takes too much space. So always think of like, what are the space that is occupied by these reactions. So in your book, they don't mention Lewis acid, but you might encounter it somewhere. A Lewis acid would be different from a Bronsted because it will be a bulky substituent. So it affects the reaction differently. And remember, Lewis acid doesn't allow us to do a carbocation, agree or not?
Yeah.
So there's no carbocation with Lewis acid. So only this works if you have what? The carbocation. Anything that doesn't give me a carbocation is going to be opposite results. Okay? Is everybody understanding this? Okay, so you're going to see it better now if we add a base. So, so base or nucleophile, anything that is neutral or negative. You all know, so for example, if I have NOH minus, it's a base, but it's also nucleophile. I can also have water. See, water is also it's a nucleophile. So anything with lone pair, whether it's a base or a nucleophile, so this is considered a base, and this is considered a nucleophile. What do they have in common? They both have lone pairs. So the attack has to come from the lone pair. So both of these, we can put them in one category. They're both considered something with a lone pair. Okay, whether they're base or nucleophile, they both have lone pair. That's what they have in common. So if I bring a nucleophile here, what's the first step? can the nucleophile attach to the oxygen? Why not? What's on the outside here? Electrons, and what's outside here? So what do they do? So a nucleophile or a base are never going to attach to the oxygen. So what do they have left? Which bond is weak here? See the CO, you agree? This one and this one. The oxygen wants to take it all. So if there is a nucleophile, the oxygen will be super happy. Why? Because the nucleophile attacks in one position and the oxygen takes what it wants. So we have two possibilities here, okay? You can have this come here and the oxygen takes the bond. That's the bond to break, no matter what. You understand this or not? That's the weakest spot. That for the ring strain, but it's also the most polar. So it's always the most polar bonds that open. It's not a CC, it has to be a CO. Is everybody understanding? So this is our blue path. But I can also have the nucleophile attack this one. And that would be my green path. So the blue path will give me this carbon, the nucleophile. So again, if I number them here, I'm going to put 1, 2, 3. Okay? So the nucleophile attaches. So this is 3, this is 2. Maybe to be consistent with the previous scenario, I'm going to put two methyls. Okay? So this would be 2, this is 3 and 4. So we have so the oxygen goes there with the negative charge, and the nucleophile attaches to carbon 2. The other option is the nucleophile attaches to carbon 1. So this is 1. Then I have carbon 2. And on carbon 2, I have 3, 4, and O minus. So the question is, which one is better? Is the nucleophile going to attack carbon 2, or the nucleophile is going to attack carbon 1? The nucleophile is a big group, you agree? So is it going to be easy for the nucleophile to make its way to 2? No. So this one is not going to happen. Why again? Because of steric hindrance. Okay? A nucleophile has to have a path, has to find a way to get there. Okay? So this is not going to happen because it's too much steric hindrance. But are we done with this one? Still have a negative charge, so what should happen now next to neutralize it? You have to protonate with the acid. So here you add an H plus and you end up with OH. You have to add an H plus. You have to have a second step. So this is, of course, protonation. So what is the difference between an epoxide reacting with an acid and an epoxide reacting with a base? Bronsted acid. Bronsted acid, if you can form a carbocation, it will always what? Form carbocation. So the first step is protonation of the oxygen, then carbocation, and then addition of the halogen. Is everybody seeing this? With Bronsted acid, you have 3 steps. First step is protonation of the oxygen, then carbocation formation, and then addition of the halogen. Now, if we don't have a tertiary carbocation, if you have a primary carbocation, how many steps you have? 2. The first step is what?
Protonation.
And the second step is
Addition.
addition. Now, in here, if we have a nucleophile, whether it's a strong base or any type of nucleophile, what is the first step? So always the nucleophile attacks and then protonation. So it's always 2 steps. No carbocation, because a base or nucleophile can form something positive. You understand? Something negative cannot have something positive sitting there. Okay, so that's the reaction of epoxides. Easy. So contrary to alcohols or ethers, epoxide reacts both with Bronsted acid and with the nucleophile. Now there are other reactions of epoxides that you need to know that are not similar to alcohol or any of that stuff. They're kind of like, some reactions are hard to kind of classify, but since they talk about epoxide, you might as well just study them. Okay, so let's see. I have this is an epoxide that's attached to a ring. Okay? So let's say I bring OH minus. This is my nucleophile. And I picked something here that doesn't have any ambiguity. So what should happen in this mechanism? What's the first step? Every time we have a nucleophile, what happens first?
Nucleophile.
Attacks, but which bond has to break? It's the CO because it's the most what? Polar. Is everybody understanding? That's the weak spot. It has to open. For 2 reasons. It's polar and there is a ring strain, so it has to open no matter what. So what we can do is we have this from here, this opens. The question is, when you have something like this is a cyclohexane. Remember, you can have axial, equatorial. Are they both up? Are they down? So here we have this different stereoisomers. You understand this? So, is there a way it's going to attack from the top or from the bottom? Do you understand what I mean? But it's not going to give us the same product. You agree? Which means, like, if this attacks from the bottom, what should happen to this bond? It has to go
Goes up.
up, up. And if this attacks from the top, this one has to go
Down.
down. But the bottom line is one has to be up, the other one has to be down. Okay? So we end up with this. So let's say this is OH came down. So this is up. So it's an addition. One is from the top, the other one the bottom. And then what's the second step? Of course, it is protonation. So you end up with a diol. This is called a diol. 2 alcohols, that's what the diol means. And with 1 BOH up, so there are trans diols. Okay? But what if I want a cis diol? So this is going to be handy for synthesis. You now know to produce a diol, you use an epoxide. But if I want a cis diol, meaning the 2 OHs on the same side, what do you use? You use an alkene. You can't use an epoxide. So, of course, you might say, this is not an epoxide reaction. It doesn't matter. All you need to understand is that the products are kind of cousins. Okay? So how do we make these 2 cousins? In here, you use osmium oxides. So osmium oxide is 4 oxygens on the osmium, and they're all double bonded. Because osmium is large, so it can have more than 4 bonds, and it goes all the way up to 8 bonds. So how does this work? This is like this, the Diels-Alder kind of reaction. So this comes here, this comes here, and this goes on the oxygen. Okay? So we end up with this. It's called a concerted mechanism. They all happen at once. So now there's an O here, an O here, an OS here. Okay? And then the last step, you have H2O2. Yes, you don't need to know the mechanism. And water. So this is hydrogen peroxide with water. But notice, where are these 2 oxygens? They have to be on the same side, you agree? So when you add water and hydrogen peroxide, this will go back to the osmium, and this will be the 2 OHs. So you end up with the cis one. So they're either both on top, and that is the method to prepare a cis diol. Okay? And then it's plus OSO4. You get it back from the oxygen in the hydrogen. So if you want a trans diol, you're going to use an epoxide. If you want a cis diol, you need to use an alkene. Okay? So now what's left on the chapter? What are the other functional groups? Sulfur containing and nitrogen containing compounds. But what did we say before? The bond, the polarity of the bond is weaker, you agree? Compared to the CS is less polar than the CO. And if I were you guys, this part, these reactions, make sure you write synthesis. Because that's where you're going to need it. It's going to be really what you need for synthesis. So let's go back a little bit. What functional group did you study before? And I'm not talking about alkenes and alkynes. You know, alkenes and alkynes are double bonds, very different. But it's what functional groups we studied before you came to this class. What was the last one you saw in chapter 9? Remember? Right. Actually, yeah, before the radical. The radical was just for alkanes. It was for alkyl halides. Remember we used this in chapter 9? And what is in chapter 10? We have alcohols. So you see, from chapter 9, you started some functional with the alkyl halides. Then you have alcohols, then you have thiols, and you have amines. Okay? So if you want to compare them in reactivity, which ones would be the most reactive? How do you approach this? What does it mean most reactive? When this reacts, what happens to it? The halogen leaves, you agree or not?
Yes.
When this reacts, what leaves? OH. When this reacts, what leaves? And when this reacts, NH. So how do I know which one is the most reactive or less reactive? It's really what is the conjugate form. Like what do I bring in? What do I get out? So if I bring, let's say here, an OH minus, I'm just going to give you one quick example. Okay? What happens if you have a halogen, alkyl halide, with an OH minus? What's going to happen? The OH will attach to R, and the halogen loses. So you end up with ROH plus X minus. So is this reaction going to happen or not? Why it's going to happen? What is this? So in order for reactions to happen, this substance is stable, you agree? This substance is stable, you agree? So what do we have to compare? We have to compare this to this. Which one is more stable? X minus or an OH minus? Why? Because this is a strong base, and this is a weak base. This is a poor leaving group, this is a very good leaving group. So this reaction will happen because this is a strong, this is weak. So it's always the strong wins. If you put something strong, it will react. If you put something weak, it's weak, it can't do the work. Is that clear? So in any reaction, when we ask you, is there a reaction or not, you always have to compare your substituents. Okay? Now, if I reverse the roles here, and I put just X minus, is this going to work? You agree it's not going to work. What did it take to make it work? What did we use?
Strong.
So it has a different mechanism. Why it doesn't work? Because if this, suppose it's working, this would be the product, okay? Is this compared to this, what happens? This is weak, this is strong. A weak is not going to give you a strong. Is that clear?
Yes.
It's only a strong that gives you weak, but weak cannot give you strong. And that's the power of nature. That's everywhere in nature. It's nothing new. Nature is like that. Strong always wins the weak. Always. But there are tricks. So now let's compare them already. What did we say about this compared to this? What do you expect? Which one is more reactive, an ROH or an RSH? ROH is more reactive than RSH. Okay? Why? Because this is, so we're going to talk about thiols in a minute. And we're going to compare them. But if I compare an ether to an epoxide, which one is more reactive? Epoxide. Why?
It's more stable.
The only reason is for ring stain, that's it. They should be same in terms of bonds, but they're different because of the ring stain. Okay, so let's look at these. So if I start with RSH and a base, whatever it is. So what is the base going to do? How is this going to react? Remember, compared to ROH? So let's say the base is can't think of one now, but so let's say it's NH3. You all know this is a base. So what's going to happen here? If I compare this bond to this bond, what difference do they have? This is much bigger than this, so which one would break faster? So if I put here ammonia, I tell you, you put ammonia in the presence of an alcohol, you can wait until 1,000,000 years. It's not going to work because the size of the bond is not that different to get RO minus plus NH4 plus. Whereas here, you end up with RS minus plus NH4 plus. Okay, so which one is more stable? RS minus or RO minus? This one is more stable because it's a bigger atom, so that additional electron won't. So thiols react better with bases than alcohols, but they're not very reactive. Even if they react better, still what? This is not too bad. This is still weak base, but they react much better than this because what? This is a much stronger what? Base than this. You all know this is a weak base, this is a strong base. So this is strong base, this is weak base. So you can't do that. You can't form a base strong from a weak. Whereas here, this is a weak base, and this is also a weak base. So that can work. They're both weak. Is everybody understanding this? So thiols work with some bases. But alcohols, it takes a very, very strong base to make them work. And I skipped that part because I want to go back to it later. Okay? So thiols can work. But then, what is then the next reaction? So they can work with a base, as you see, and it gives you something negative, like that. Okay? And ammonium salts are pretty stable. They're very, very stable salts. And then you can take that. And then what if I bring R prime Br, let's say, and I'll kill halal. See, in here, this is easy. This takes this, this takes off. Why? Because Br minus is still more stable than RS minus. So you end up with RS R prime, which is a thioether. So you start with the thiol, you end up with a thioether. So thiols are good to produce thioether. That's it. And they're both nasty anyway, and they stink. So I told you, most people don't even work with these. But you have them in your body, so sulfur compounds, they exist in some proteins in your body. They exist also in some sugars, not really that many, but the proteins in your body and amino acids, you have some sulfur that really is important in many ways, especially like your hair. You know, the hair has a lot of SH bonds, lots of them. Okay, now you see that the thiol give us the thioether. But you know what? The thioether, you can also add another alkyl halide, and it would produce R S R prime so this is just like quaternary ions, this is called sulfonium ion. So sulfur can add up to 3 alkyl groups. If it has 1 alkyl group, it's a thiol. If it has 2, it's a thioether. If it has 3, it's called sulfonium ion. Just like nitrogen, see, nitrogen, when it's all like this, you can make it into NH2R, then it can go to NHR2, then it's NR3 to NR4+. So thiols and amines, you can remove H and replace it with R, remove H and replace it with R. So you go from ammonia to primary, to secondary, to tertiary, to quaternary. Okay, so this is primary, this is secondary, this is tertiary, this is quaternary. So amines, you can remove an H and put an alkyl. Just the thiols, you remove 1 H and put an alkyl groups. Okay? Now, these are very good compounds because then you have a good leaving group. Because this is too bulky, just like carbocation, tertiary carbocation. This looks like a carbocation with 3 bonds. So these, usually, if you take them, and then let's say I use OH minus. See, this is a weak base, but if I use a strong base, what can happen is this takes 1 of the R, and this takes the double bond. So sulfonium ions can give you a thiol, ether, and an alcohol. Okay. That's all you need to know about sulfur-containing compounds. So I'm going to build something on this side. The first one is alkyl halides are the most reactive. And to be in particular, like RBR, I'm sorry. So I is more than BR, which is more than CL, which is more than F. Because of the leaving groups. The next are the epoxides. Doesn't matter how many substituents. So epoxides are more reactive than alcohol. So everything we did for alcohol works for epoxide in terms of substitution. Okay? And they work with Bronsted acid, also Lewis acid. The only difference is Lewis acid will open it on the less bulky side. Then we have the alcohol. Then we have the ether. Then we have what? the thiol. Then the thiol ether. And then what? The last category are amines. So what does it tell us if they are the last one? We don't have much to study about amines. We use them as a base. Okay? Okay, so they're used as just bases on nucleotides. So if you need a nucleophile or a base, just throw them in. Now, if you look in the book, even though here, this chapter, it says, the title says, alcohols, ethers, epoxides, amines, and sulfur-containing compound. But if you look at the back of the book at the end, they only put one reaction with nitrogen. So why did they put only one? Because that's the only one that you see in this chapter. Everywhere else, amine will be a nucleophile or a base. Okay? So a base is a base is a base. We're not going to put a chapter on OH minus. You understand what I mean? OH minus is OH minus. So if you see an acid, it's going to react with an OH minus. Same thing with amines. The only difference is they're not strong bases. We already know they're not strong bases and they're not very reactive. So the only thing they can do is be weak bases or nucleophiles. So we'll see them as something that comes back as just a nucleophile. So what is then the reaction that you need to know in this chapter? Only one, which is the Hofmann elimination. Now, another thing I want you to think of doing, every chapter that has names of a reaction with a name, please make sure you know it, because these are important reactions. So if it says Suzuki reaction, there's a name there. I need to know what it is. If it says Hofmann reaction, I need to know what it is. If it says Williamson reaction, I need to know what it is. So any reaction with a name, you'll see it. There's a Michael reaction. There's every time you're going to see a reaction with a name, you need to know what it is. If it doesn't have a name, you need to know some mechanism, but they're not as major as the reaction with the name, because they're major in terms of chemists use them a lot. The guy probably got a Nobel Prize because it has an effect on many other reactions. So remember that. Hofmann here it has a name, somebody, so we need to know. So how does it work? So how does it? The Hofmann reaction works is, so it's a quaternary amine, okay. So I have here, now notice, what I write is very important here, okay. You need to have 2 carbons right there, okay? In the presence of a quaternary amine. That's a quaternary amine. Just like I showed you earlier, you add 1 alkyl group, 2nd alkyl group, 3rd alkyl group. Now, if I bring a normal OH minus, okay? So, can this happen? comes here, this takes off. So one could think R, CH2, CH2OH, plus another amine, primary amine. So this is a strong base, you agree? This is a weak base. So, can this work? The answer is it won't. Why? This won't work. Because the nitrogen, the more alkyl group you add to it, the more you stabilize it. So quaternary amine is more stable than the tertiary amine. Okay? So we're not going to look at which one is a stronger base because we can't compare base to base. All we're going to say is this has 4 alkyl groups. And these 4 alkyl groups, the more you put alkyl groups, the more you stabilize the nitrogen. The less alkyl group, the more reactive it will be. So ammonia is more reactive than any primary amine. Primary amine is more reactive than secondary. Secondary is more reactive than tertiary. And quaternary amines are very stable. Once you form them, they're happy. They're not going to give you anything. They're going to be very, very stable. So that bond there is not going to break. Okay? So you can't break the CN bond from a quaternary to a tertiary. The question is then, what is Hofmann reaction? If I put the OH minus, where is the OH minus going to attack? It's not going to add here because this bond is not going to break like that. So where is it going to, how is it going to work? It works better if you have an elimination, okay? So it's an anti-Zaitsev rule. So what happens here is the OH minus this won't happen by itself, as I said, because this is stable. So you have to have a driving force, something that forces it to get out of there. So what can force it to get out of there? You have to have here a CH, and then I have an OH minus. Now, this has to take off because it becomes a conjugated system, but you'll see. The OH minus here, if it takes this hydrogen, then we form a bond here, then this carbon will let go of that bond. So the carbon won't let go of the bond unless it's within the system. But the bromine is not, or anything else that I put here, the OH minus is not going to approach this. But in here, it will work because this is forced to go here, so this carbon now has to give away that bond. So it's driven by elimination. So a quaternary amine is not going to react unless you create an elimination. Okay? So it can be a substitution. There's absolutely no way a quaternary amine will be substituted. You have to have an elimination. So what is the product? It's going to be R, CH, double bond CH2, plus the tertiary. Here it's forced to get out. The carbon will kick it out because it can't have more than an octet. Okay? So substitution on a quaternary amine doesn't work, but elimination, it's driven by elimination, but where does the elimination happen? You see, this is the alpha position from the nitrogen. You learned this is alpha. The first position is alpha. This is called beta position. So you have to have an H on the beta position to get that quaternary amine too. Okay? If you don't have this, you're not gonna have, it's not gonna work. So quaternary amines, they don't react, they're super stable. The only time they react is if you use what? A strong base that drives. Okay? Now let me give you another example. So is everybody understanding this? The quaternary more stable than tertiary. That's why substitution is not going to happen. But if it's an elimination, it will happen just because, you form a double bond here, so that's driven by the double bond formation. So let's try a few examples. And this is, by the way, to remember this. Remember how chapter 9, we always say that elimination and substitution, they compete? This is the only situation where they don't compete. It's either or. So for quaternary amines, you can't have substitution. All you can have is elimination. Okay, so here are two examples. Or one, maybe. We'll see. So here we have this. CH2, H. Yeah. CH. So you see, this is my alpha. You see, this is the beta. This is the alpha. This is the beta. So I have two options. I can have BOH minus attack this one. Okay. I'm gonna put blue here. Or it will attack this one. And I'm going to put the green, of course. So, the blue mechanism, BOH minus, it's a base, so it takes this H, this folds, this leaves. The green mechanism, this attacks, this folds, this. So the blue gives me what? Gives me CH2, double bond CH. Remember, Hoffman is always going to give you an alkene, okay? And then I have CH2, CH3, plus of course N CH3. You see that? My double bond on the first and the second. This one will give me CH3, CH, CH, CH2, CH3, plus N CH3. So, which one will be the major product? The green or the blue? Why? Not here. No. Why? Yeah. So what is the pseudo intermediate? Okay, so you say this is negative, okay? So what is it gonna do? When this takes this carbon will become slightly, partially what? No, because the OH takes the H, so this carbon will partially take the electrons. You agree? So it's a pseudo-carbanion. Remember? Something negative, it's carbanion. But when it comes on this side, it's this one that's a pseudo-carbanion. And what you learned is everything that applies to carbocation, it's the opposite in terms of what? Carbanion. So what is carbanion here? Which one? Primary. And what carbanion is this? Secondary. If there were carbocation, which one is more stable? No, but between these two, which one would be more stable? The secondary. But because they're carbanion, it's the other way around. So this is a primary carbanion, and this is a secondary carbanion. So this is more stable. So this would be the major. So this is called anti-what? Zaitsev. So normally, we like to go with the most substituted, but it's not always the case. If your intermediate is a carbanion, it means the one with less substituent is the most stable. So that covers the entire chapter.